So let me start right away. And thank you very much for the previous speaker and all of you for discussing biocatalysis. That helps me to put a bit of context to my talk. Well, biocatalysis has several advantages over the more traditional chemocatalysis, namely chemoselectivity, regio and diastellar selectivity, and also enantiomer selectivity. Not to forget that these enzymes work on milder conditions and normal pressure, so it's a more environmentally friendly reaction. They're mostly used in asymmetric synthesis and in kinetic resolution. The enzyme that I'm going to talk to you about is a myoenzyme, and it is really special amongst other enzymes because it has a catalytic electrophile in its active site called a Myo group, and it's autocatalytically formed after translation from these 3 amino acids. So it's really similar to the modified amino acids that we find in GFPs. However, it's only an electrophile, and it's really a potent catalyst for this reaction. So the natural reaction is the non-oxidative ammonia elimination from phenylalanine or other aromatic amino acids. But the related enzymes, aminomutases, can catalyze the readdition of ammonia in the beta position. What's interesting in these enzymes is that whilst both aminomutases and ammonia lyases are really enantiospecific when it comes to the alpha-phenylalanine, they only accept the L-phenylalanine. There are both R and S selective aminomutases. Their application is in the reverse reaction, because by adding large quantities of ammonia, we can shift both reaction to the addition side and thus have an enantioselective reaction. Why are we interested in these compounds? Well, they are really interesting building blocks in several drug molecules like Taxol that we use for chemotherapy. And then in this way we can synthesize these drugs in a more environmentally friendly way, generating less waste. Looking at the reaction, there is more and more evidence that the reaction proceeds via an N-myo intermediate when there's a covalent bond between the methylidine carbon bond of the prosthetic group and the amino group of the substrate. And then in a second step, these 2 bonds are broken and the proton is accepted by a tyrosine that lies on a really flexible loop just opposite of this modified amino acid. So in the protein that I'm going to talk to you about, clostridium crispum phenylalanine ammonia lyase, this is tyrosine 110. The current structure in the PDB for this enzyme contains this loop in a loop-out conformation where this residue is really far from the modified amino acid, the catalytic electrophile. So clearly this structure cannot be a catalytically active conformation. We suggest that based on homologous enzymes that this might be, the looping conformation might be the catalytically active one. However, all eukaryotic phenylalanine ammonia lyase structures in the PDB either contain this loop in this loop-out conformation, or the loop is not visible. So it's a really crucial question of how this loop looks like in order to see exactly how the enzyme functions and how it binds substrates. So first we determined the binding affinities for several compounds. And we did kinetic studies and ITC studies for the various ligands. And the kinetic studies are always shown in orange background, whereas ITC is shown with the red background. So looking into the natural substrate, we can see that although enzyme does not catalyze ammonia elimination from D-phenylalanine, it can still bind it almost at the same extent as it can phenylalanine. After that, we looked into 2 inhibitors, substrate analogs, where the phosphonic acid group replaces the carboxylic acid group of the substrate. And we found that the same enantiomer, the OR enantiomer, as the natural substrate, binds 1 order of magnitude stronger than the natural substrate and efficiently inhibits the enzyme. The big surprise came to us when we tried the mirror image enantiomers. And we found that when the methylidine group was present at the beta position, the binding increased by even one order of magnitude, and the enantiomer preference of the enzymes was shifted towards the S enantiomer. So in order to investigate what the molecular origins of this interesting phenomena is, we crystallized these two molecules with the enzyme. Our first attempt, we really struggled a lot to get this protein to crystallize, and our first breakthrough came when we added this really strong inhibitor to a crystallization trial, and quite likely it stabilized a flexible loop. Well, we found out that this is what it did. And then we did a second approach, is that we cloned the enzyme to a different vector and attached a cleavable histag. And this greatly enhanced the crystallizability of the protein. And this was a surprise to us because one monomeric unit of the otherwise homotetramer enzyme is 720 amino acids long, and the histag was only 25 amino acids long. So it was kind of completely unexpected that it will have such a big effect. Nevertheless, we got a really stable and robust crystallizable system, and we could use it to co-crystallize it with many different ligands. These three probed the natural reaction and how enantiomer activity works in this protein. We also co-crystallized it with L-tryptophan, that we know that this enzyme binds but does not catalyze. This is the only aromatic amino acid that myoenzymes do not cleave. And then we also probed some non-natural substrates. The last 5 are still under refinement, so I'm not going to talk to you about those today, but only about these 4 structures. So the one complex with this inhibitor, these 2 molecules, and then the apo structure. What we learned from these crystal structures is first about the loop dynamics of this really important flexible loop covering the active site. We found that when we have a really strong binding inhibitor, the electron densities of the loop are nicely visible, and it is, as we sort of suggested before the study, it is in a loop in closed conformation. However, when there's only a weak binder or an apo structure, the electron densities are much weaker, and it is really difficult. Well, in the apo structure, it was impossible to assign coordinates to these amino acids. And in the weak binding case, there will be only a partial loop present. So we can see that upon binding, this loop, the flexibility of this loop changes greatly, and that we prove that the looping conformation is the catalytically important one, the one that is responsible to the reaction, and that the loop out, and throughout our trials, we never found any experimental evidence for the loop out conformation, and we suggest that it is a functionally not important conformation, even if it is present in solution. So when we look into this looping conformation, as I mentioned before, in the eukaryotic phenylammonium lyase structures, the loop is not visible. Compared to the prokaryotic structures, when the loop is nicely visible, even if no interacting partner, even in the apo structure. So if you look at the kinetic parameters, you can see that the eukaryotic enzyme is much faster. It's a better biocatalyst, and it is possible that this loop flexibility is the key to this of this faster reaction rate for the enzyme. After investigating the loop conformation, we looked into the binding conformation of the enantiomers. And when we investigated how these inhibitors bind in the crystal structure, we actually saw a covalent bond to the catalytic electrophile. So this is a direct proof, the first one for phenylammonium lyases, that this reaction proceeds through an N-myo mechanism. If we overlay the 2 structures, we can see that the aromatic group and the phosphonic acid group of the two inhibitors bind in the same way, and the main difference is in the C-beta position. Based on these two structures, we modeled the binding of L and D-phenylalanine in the structure and suggested that maybe by modifying the binding of the carboxyl group, we can change the position of this beta carbon atom and actually make the enzyme eliminate ammonia from D-phenylalanine as well. So we selected these three amino acids and created a limited site saturation library. So the rationale behind this is that we still want these amino acids to fulfill the role of coordinating the carboxylic acid part of the molecule. However, we wanted to do it in a different way. So this is why we selected residues that can either form an ionic interaction or a hydrogen bond to our residues. After that, we created the library by using PCR reactions and transformed the plasmid into protein-producing E. coli cells, and then picked colonies into a 96-well plate, and then transferred them into an autoinduction media in a deep well block, lyased the cell, and measured the ammonia lyase activity directly from the supernatant. And we decided that we're going to say that we found a hit if the D-phenylammonia lyase activity compared to the L-phenylammonia lyase activity is superior of that of the wild-type protein. Unfortunately, I cannot show you any results of the screen of this library because we encountered some difficulties in the library creation with the PCR reactions, and therefore I couldn't get these results yet. So to summarize what my talk has been about is that we used two different strategies to obtain crystals from our target protein, and we actually measured 8 different structures co-crystallized with ligand from those I've shown you, like these 3 in detail. Based on the refined structures, we concluded that eukaryotic phenylammonia lyase have a really flexible loop that is stabilized upon ligand binding and upon catalysis. And based on the binding of the mirror image enantiomers, we came up with a semi-rational library design for altering the enantioselectivity of these proteins. So with that, I would like to thank my supervisors, Dr. Beata Virtes and Dr. László Poppel from the Budapest University of Technology for helping me with this work and asking the questions. I would like to highlight Ibolya Leveles, who is here in the audience today, who helped me a lot with crystallography and structural reform.